we are going to do balancing and predicting products. Predicting products, balancing equations, getting net ionic equations. So we're going to learn a simplified way. Notice this is a solution of. We notice the sodium and the nitrate. That says there's going to be double displacement. The sodium and the hydroxide are our spectator ions. So the hydroxide is OH minus, and the lead is Pb2 plus. When we put those together, we're going to get solid lead 2 hydroxide. We need to balance this. There we go. That's my balanced net ionic equation. Now I need to look at the question. Notice I have the same volume, same molarity. That 1 liter, 1 molar would give me 1 mole of each of these. But note, it takes 2 of these for every one of these. So right here is my limiting reactant. 1 mole of that is limiting. I only need 0.5 moles of this. And I will only be able to make 0.50 moles of lead 2 hydroxide precipitate. And there's my answer. All right. Excess nitric acid is added to solid. Okay, this word solid, I automatically know I need the entire formula, calcium carbonate. You got to know all your ions, charges, and be able to balance those. And we've got excess nitric acid, which we'll split apart. Now that word excess, that doesn't mean that we have a ligand problem, because nitrate is never a ligand. Nitrate is soluble, it's never a ligand. So the nitrates, you should recognize it's not going to do anything here. All I care about is my H+. So that tells me my H+, remember the positive ions switch places. So the H+ and the Ca2+ are going to switch places. So I will get H2CO3 and Ca2+. You could go through the whole molecular equation to get your net ionic. But if you recognize that the NO3, the nitrate, is just going to be a spectator ion, you go straight to the net ionic equation. Okay, now is that balanced? No. I need 2 H pluses over here in order to balance the H's. Now they said excess, so you should also remember that when you have excess acid, your carbonic acid will split into water and carbon dioxide. So now we have 2H plus, and calcium carbonate makes water, CO2, and calcium ions. Now, so that's my final answer. There will be a box. You put that answer into a box. Why do statues made of calcium carbonate deteriorate? Okay, so you want to think, what's deteriorating the calcium carbonate? And it has to do with this reaction. So it must have something to do with H+. So you should be thinking you're outdoors, you're in an urban area, we've got acid. What do you think of? You say acid rain solubilizes, or acid rain deteriorates. Or dissolves, deteriorates the calcium carbonate. Or acid rain reacts with the calcium carbonate in the marble, and it turns it into water and carbon dioxide. Anything like that will do. Okay. Now this time we're told we just have silver ion. In another solution, we've got iron ions, iron 2 ions, and they don't tell us anything else. We know that this is going to get reduced because it's an oxidizing agent, and this is going to get oxidized. They told us it is a reducing agent. Those are very important things here. They give you some information. Okay, to get reduced, the charge goes down. Well, if the charge of this goes down, the only other thing that silver can be is 0. And to get oxidized, it's a reducing agent, so reducing agents get oxidized. So that means the charge goes up, And the only other charge for iron that I know of is 3. If you're trying to pick a charge, just pick something that makes the iron increase. And most of the ions that we work with don't go above 3, so it's a logical guess that we would have the iron 3. Now it is actually balanced because the total charge on the left side is 1 plus 2, the total charge. And the total charge on the right side is 3, and 1 equals 3. So we're balanced. We're good. Now the question. If the contents of the reaction mixture are filtered, what substance would remain on the filter paper? Well, the ions, the silver and the iron ions, they're not going to stay on the paper. They're dissolved. However, right here, solid silver stays on the paper, the filter paper. New problem. Solid. All right, we've got solid, so we have to include the whole solid thing. Ammonium, NH4, carbonate, CO3. We have to balance our charge. CO3 is -2. So ammonium carbonate decomposes as it is heated. You don't have to mention solids, liquids, or gases. Oh dear, what is this going to decompose into? Now, just going off, I'm not saying this because I know the answer, but just looking at this, if I heat this up, I notice there's some CO2 in there, so I would just think we're going to make some CO2. And I notice in this ammonium, I could get some ammonia, NH3. But then I have only an HO. Okay, so that's not going to work. So I should get some ammonia off of here. And actually it would work, you'll see in a minute. There's different ways to think through this, but I want you to hear what process my head is going through. So I think I've got some ammonia there, and maybe I could have some H2CO3. Will that work? Let's think about that for a minute. Okay, you got to notice there were 2 ammonia, so I have 2 of those, and 1 H2CO3. It looks like I'm okay. But notice this H2CO3, remember if we heat that up, we could get H2O and CO2. So originally, I could have just gone straight to the H2O, CO2, and NH3. I hope that's the right answer. I'm going to check it real quick. This is what my guess would be. Okay, so I checked, and in fact, we need the 2 right here. We've got to balance out that 2. I forgot to put the 2 up there. And that's what we get. Now notice, I was just thinking, when I heat something up, I should produce some gases that I'm familiar with. So I was just looking for gases that I could make out of this substance here. Okay, so predict the sign of delta S for the reaction. Explain your reasoning. Well, this would be a gas. CO2 is a gas. Water would be a gas. If I'm heating it up, I'm not going to get liquid. I would heat it up so much. I'd get water. And since I'm making 3 moles gas, I make 3 moles gas from a solid. That means entropy is increasing, so delta S is greater than 0. All right. Whoa. Okay, chlorine gas. I've got a gas here, so I can't break anything apart. Oh, and it's an oxidizing agent. So this is going to get reduced. It's an oxidizing agent. Is bubbled into a solution of potassium bromide. Potassium bromide. So I have to think, will the K plus or the Br minus react? Well, chlorine is a nonmetal, and bromide is a nonmetal. So most likely, I'm going to have the nonmetals just reacting with each other. So bromide. Well, if something gets reduced, something else has to get oxidized. So the bromide would get oxidized, and if chlorine gets reduced, reduction, we're going to gain electrons, it becomes Cl minus. The bromine gets oxidized, the charge has to increase, so we would go from Br -1 to 0. Now Hofbrinkel, Br2. When bromine is by itself, there's always 2. And chlorine, hopefully you remember to put the 2 right there for the Hofbrinkel. Now we have to balance 2 and 2. You check your charges to make sure the charge is balanced. On the left side I have -2. On the right side I have -2. I'm good. Okay, there's my reaction. What is the oxidation number of chlorine before the reaction occurs? Before oxidation, the chlorine oxidation number is 0, and after, oxidation number of Cl is -2. Okay, done with that one. So notice, this isn't like just double displacement, single displacement. What do we have? We're just looking and thinking logically through this. Okay, small piece of sodium. We've got pure sodium. And it's not ion, it's sodium metal, so there's no charge. Beaker of distilled water. Wow. I'm just reading. This thing burns and produces flames. Let's see what happens. Okay, Na plus H2O. Now, the only thing that can happen here, I have an element and a compound, so I have to have single displacement. I don't see anything else that could happen. And positive ions, well, things that can be positive will switch with things that can be positive. So the Na will switch with the O. Oh, and first, my first guess would be this. So I would get Na2O, and then hydrogen by itself, but we have Hofbrinkel, so it has to be H2. Now, there's another thing you must remember. There's just a very important little piece here. Whenever we have sodium oxide in water, any oxide in water will produce the metal, any metal oxide. Metal oxides plus water will always make the metal hydroxide. Okay, that's what you always get. So the products here, we can't stop right here. We have to keep going. This Na2O will actually go all the way to NaOH because we have a sodium, which is a metal oxide. Metal oxides in water will always make metal hydroxides. Now I have to figure out how to balance this thing. So if we look carefully, you will realize you need 2 NaOHs, and we need 2 waters and 2 NAs. I'm pretty sure that that is balanced. Yes, it is. Okay, so I'm going to cross that out. Here's my balanced reaction. Okay, and when this reaction occurs, it is very exothermic. Sometimes small flames are observed as the sodium reacts with the water. Which of the products of the reaction burn to produce the flames? So here they're also giving you a hint that something is over here. There's something in these products that will produce flames, and hopefully you know hydrogen. Hydrogen produces the flames. When you burn hydrogen, when hydrogen gets really hot, you will get flames. All right. Okay, new question. Aqueous. We've got aqueous sodium hydroxide. So there's probably going to be some spectator ions here. Is added to a saturated solution. Now, we said saturated solution, that means I've got solids. When you say a saturated solution, they're telling you that this stuff is insoluble. So I cannot split the aluminum hydroxide apart. Oh dear. So first, let's look at this. We've got NaOH. Now I know what's going to happen here, but just looking at this, we can't just switch the metal ions. That doesn't make any sense. So that's not going to happen. So I've got hydroxides and some metals, and we said most likely this sodium is just going to be a spectator ion. Almost always when you see sodium, unless it's just sodium by itself as metal, the sodium is going to be a spectator ion. So now look at this. And it didn't say concentrated, but let's look at this. would the concentration of the complex ion, oh no, they told us right here, we form a complex ion. Okay, you know about complex ions. And let's go with our simplified rule. There are several different complex ions we can make. We are not going to make the most common one because it's too hard to remember. So we will make the complex ion, remember the charge is going to be twice the charge of the cation. And this cation, Al3+, has a charge of +3. So that means we will have 6. 2 times 3 is 6. So we will have 6 ligands attached to the aluminum ion. Now, aluminum is +3, and hydroxide is -1, and we have 6 of them, so the total charge here is -3. Let's balance this out now. I've got 3 hydroxides here. I need 3 more. There's my balanced reaction. And if the resulting mixture is acidified, we add some acid. What would happen to the concentration of the complex ion here? So, if we had H+, we add some H+, and the H+ reacts with the OH-, which means we are removing some OH-, and apparently this reaction is reversible. So, by Le Chatelier's principle, I just misspelled that, put too many I's in there. IER. By Le Chatelier's principle, let's see what happens. The reaction goes left, and the complex ion concentration goes down. Now, they did not ask you, oh, they did ask you to explain. So you can't just say it goes down, you have to explain why. All right, 2 more. All right, we'll do a couple more. Okay, hydrogen chloride gas, HCl gas, is oxidized by, okay, so this is getting oxidized by oxygen gas. And so that means the oxygen gas is going to get reduced. Okay. Hydrogen chloride gas gets oxidized. The O2 gets reduced. We're going to make O2-, and because the oxygen has to get reduced, and something gets oxidized over here. So we have a +1 and a -1. To get oxidized, that means your charge increases. Well, the hydrogen can't go up anymore. We can't have an increase on this, which means this is the only one that can increase. And when Cl goes from -1, it would go, to get oxidized, it would become Cl0. And remember, we have Hofbrinkel. So, what else do we have here? We have some hydrogen still on the left. We're not allowed to split this hydrogen chloride gas because it's in the gas phase. So it's not, there's no liquid in here. There's nothing going on. So we need to keep the HCl together. So I also need to have some H+ as a product. Oh, and look at that. Now, when we have this right here, you should recognize that you're going to get water. When you have O2- and H+ together, they always come together to make water. So we'll have HCl and O2 to make H2O and Cl2. And now I have to balance this. And notice, this is not a reaction we would ever have gone over before. It's just, you just have to kind of guess what's happening. There is one other way. I'll show you another way to think about this one. But first, let's try to balance this. We had 2 H's and 2 Cl's. But there's 2 O's, so I need a 2 here for my 2 O's that are here, which now makes this 4 HCl's, which means I need 2 Cl2's. And that is balanced. Okay, another quick way to think about this one. If we have HCl and O2, nonmetals switch with nonmetals, or the things that are negative are going to switch with the things that are negative. So that means that these two, it's a single replacement reaction because I have an element in a compound. So it actually was predictable. So the H goes with the O and we get H2O. And the Cl goes by itself, Hofbrinkel, so we know we need Cl2. And notice if I look at it that way, I get the same exact reaction, and then I still have to balance the reaction. 2, 2. What's the question? If 3 moles of hydrogen chloride gas and 3 moles of oxygen react as completely as possible, which reactant is present in excess? Well, just looking at this, you need more hydrochloric acid, hydrogen chloride, than oxygen, which means HCl is the limiting reactant because you had equal moles but need more HCl. All right, last one for this video. This video is getting long. Solid potassium oxide, K2O. We can't split that apart because they told us it's a solid. It's added to water. Now remember, I just told you this is so easy. Whenever you have a metal oxide in water, you will always make the metal hydroxide. That's all you make. So I'm going to make the metal hydroxide, KOH. OH is -1, K is +1, so KOH is the correct formula. And let's see, what else do I need? I need to balance this. I'm going to need, I think, more than 2 of these. I think I'm going to need 4 of these. Let's just see. If I have only 2, I have my 2 H's. Oh, no, I just make 2. My H's are balanced, my O's are balanced, and my K's are balanced. There's my reaction. This is not my net ionic equation because this KOH will split apart. This is in water. So the K2O is solid. I leave it alone. And my actual final products are 2K plus 2OH minus. There we go. There's our balanced net ionic equation. A few drops of phenolphthalein are added. What would be observed? Okay, this solution is going to be basic. Basic solution because of the hydroxide. So the phenolphthalein makes the solution. You need to know these colors. Bright magenta or pink. Pink is okay, but we get that really gorgeous magenta color.